Good afternoon, everyone. Welcome back. Hope you had a wonderful morning and a very good breakfast. Today, I'm going to be discussing about how to analyze randomized algorithms. In the previous lecture, we discussed about what are randomized algorithms, where we can use random variables in what kind of situations we can make use of those random variables and optimized our algorithms. Today we're going to be discussing about how we can analyze the complexity or how we can estimate the runtime of randomized algorithms. Before we start, let's discuss an important concept of indicator random variable. Let's say we are given a sample space S and an event A, then indicator random variable IA is defined as IA equal to 1 if event A occurs, IA equal to 0 if event A doesn't occur. Event is simply means that let's say you toss a coin, and so there are two events possible, head or tail. So let's say if the event is if you want to get the head, so what gonna be the indicator random variable for that event that you get head. So let's say indicator random variable, you get head on a flip of coin. Then you just define 1 if head comes and 0 otherwise, right? Now, in simple sense, what we can do instead of writing a big expression, we can simply say that a random variable x for the event that h comes on the top. We can define like that. Good. Now, following the same in the same line of discussion, that let's say xa is the indicator random variable or random variable for the event A. If the event A happens, then the expectation of the random variable xa will be equal to the probability of happening the event A. This is a lemma, which is you can see in probability theory books. So for randomized algorithms, or wherever we're going to use random variables and we're going to do analysis, it is a good idea to take a basic course in probability theory or some familiarity with probability and expectations, how to calculate expectations. But those who haven't done any course in probability theory, don't worry. We're going to be defining simple concepts, and we're going to be learning. So that's not a stopping point for learning randomized algorithms. Just pay attention, be patient. Now let's talk about an example of quicksort. So quicksort, you might have seen in your textbooks or at many other places. You might have read. Say you have given a list of numbers which are in random order, and you are asked to sort that list. So quicksort is an algorithm or a way of sorting the list quickly. So we're going to use the divide and conquer approach here. I discussed divide and conquer approach in previous algorithms lectures. If you haven't watched it, I would recommend you to watch my previous lectures on quicksort. But here, very quickly, let's say what it is. So far, we discussed about deterministic quicksort. So we're going to review it again here. So let's say you have been given a list of numbers. distinct numbers which are not sorted, and your output you want in ascending order, a list L sorted in ascending order. So what an algorithm we can write here? Simple steps. If you have just only one element in the list, then you just return that list. That becomes your boundary condition. Otherwise, let's assume that you take one variable which is equal to the a1, some element in the list. For simplicity, we just choose the leftmost element, or first, or you may choose any element. So that's a variable. Now you split the list such that the elements which are less than z are in L1 list, and the elements which are greater than z are in L2 elements. And how you do? You compare each element with g, and if you find, okay, this is less than any element, say ai is less than z, you put it in L1, and ai is greater than z, you put it in L2, and then you recursively sort both the lists L1 and L2, and in the end what you're going to return is the sorted list L1 dot z becomes your middle element dot sorted list L2, and you're done. And we have seen earlier that the time complexity, or the worst case number of comparisons this algorithm will take, will be order of n square. Good. So order of n square is a kind of very expensive in terms of time, running time. Can we do a better job here? What do you think? What do you think where we can do some magic? Think about it for a second. Okay. How about we choose z randomly instead of taking a fixed number here, or taking an element from the array from a fixed location. How about we randomly choose that element z? Can we do a better job? Since we're gonna choose randomly, so we are involving some sort of a random process here. So in computer terminology, we call a pseudo-random number generator, which generates a random number between 1 to n, and then we call z equal to a of, say, k. K is generated by your pseudo-random number generator. Means that we pick up that position from the array, and we pick up that element from that position from the array, and that becomes your pivot element z. Good. So let's say whether this can improve. So it's a simple difference. Everything is same as your deterministic quicksort algorithm, except instead of fixing your z, which is a pivot element for comparison, you are now randomly choosing z from list L. Now, because now you are randomly choosing, so what kind of distribution you're going to use? In most of the cases, we use uniform distribution. But if you find out that, okay, some other distribution may give you better results, you may go ahead and choose that. But for here, for simplicity, we're going to be using uniform distribution. Okay. Now the same process, you split the list into two parts and put elements in the L1 list such that element is less than z, and the elements which are greater than z, you put it in the list L2. And the same process, you recursively call randomized quicksort algorithm on L1 and L2, and in the end you get the sorted list L1 and sorted list L2, and you join together with the z element in between. Easy. Isn't it easy? It's very easy. There is no difficulty here. It turns out to be that if we do this way, our worst case time complexity is order of n log n, or n natural logarithm of n. Good. So far so good. Now the important question is here how we get this number O of big O notation of n log n. So we're going to be working on that. So that means that we need to do analysis of randomized quicksort algorithm to get this number. Let's see how we can do that. Okay, simple. We define an indicator random variable for that. So let's define an indicator random variable xij, where I and j, some pair of numbers which are to be compared such that I is less than j. And if the numbers bi and bj are compared immediately or in your any of the recursive call when you run a recursive quicksort algorithm on input list L. So if that happens, if you compare bi and bj, then you say, okay, the value of my indicator random variable is 1. Otherwise, it's 0. Good, understood this? Great. Now define x. Just x is the random variable representing total number of comparisons made by RQ, right? So if we can get the total number of comparisons made by RQ, we can get the idea about or we can represent time complexity in big O notation. What is time complexity? In other words, that we want to know what is the upper bound on runtime. Here the comparison is variable, it's not constant, right? So we want to know what are the total number of comparisons made by your recursive quicksort algorithm. Now those number of comparisons are gonna be random. You don't know, your algorithm might make, let's say if you have 5 elements, so it might give you a result in just 3 comparisons or sometimes 4, depending upon your pivot value, what you choose. So here for randomized algorithms, we talk about in terms of expectation or expected number of total comparisons made by your algorithm. So let's see how we can calculate that. So we calculate how we can calculate that. Expected value of random variable x is given by this formula that you do summation from outer loop I equal to 1 to n, and then inner loop j equal to I plus 1 to n. You're going to be running 2 loops in quicksort algorithm. Now next, how we can move e inside the summation sign. We can write it that way. And then what is the e of xij? What is the expected value of this random variable xij? Is simply that x into probability of xij. Now x is the value which this random variable will take. So let me write something here. So expectation in simple sense of a random variable we write it, the value which this random variable take x into probability of happening that event, or probability of happening the x. Okay. Okay. So same way we can apply the principle here. So probability of happening, sorry, here is x. So xij equal to 1. So when xij will be 1, what is the value xij random variable will take? That is 1. And then what is the probability xij? Probability xij equal to 1. And this way, and this random variable can take another value too, which is 0. So 0 multiplied by pxij when it is 0. Okay, this gives us only probability when xij equal to 1. So far so good. You are with me? It's a simple, very simple equation. Now, what is the probability of variable xij to be true? Okay, it turns out to be that 2 over j minus I plus 1. So we're going to come back to this after I define few more terms, but for now just see that probability of the random variable taking the value 1 is 2 over j minus I plus 1. Now it's very simple, you just get the summation and you get the answer. How we can do that? We can substitute a variable k instead of j, make it more simple, and then it would be always less than 2 times equal to log n. We got rid of 1 over k, and this whole term summation k equal to 2 to n minus I plus 1, it will always be less than equal to this one, and then this will be equal to this will be equal to 2n log n. Good. So that's how we got the worst case number of comparisons would be n log n, or in big O notation we can say the complexity, time complexity would be n log n, worst case time complexity, upper bound. Good. Okay, so now we go back to from where this number comes, 2 over j minus I plus 1. So let's see, during the execution of recursive quicksort algorithm, there will be a unique recursive call rqtick. Tick here means that now you are recursively calling the algorithm and your input list is now different, for which input list ltick means either it can be L1 or L2, or maybe when you go a step later on. So ltick is represents that's your original list is changed now, because you have partitioned the array and you are calling the original algorithm in a recursive call. If you're not familiar with recursion, how do we use that? I would recommend you to watch previous lecture on recursion. So for here now, so what we are saying here that so there will be a unique call for which your input list ltick will have both bi and bj numbers, but none of the sublists L1 or L2 will contain both of the bi and bj. Good. Then second note here we have that ltick, your list, it must contain all the elements from Bi up to Bj. Good. And your pivot element, which you're going to choose in your list LTIC, it must be chosen among one of the Bi up to Bj, okay, such that must be chosen among one of these. And how many of total numbers these would be? These would be from Bi to Bj would be j minus I plus 1. Good. So that's how this number here comes, j minus I plus 1. That is your total permutation for choosing your pivot element j-tick. Good. And it is chosen such that your Bi and Bj are not put in the same sublist. Otherwise, there will be no comparison, and we say the value will be 0. So to make a comparison or to get this random variable xij get a value 1, this Bi or Bj, either of these must be z, or in other words, if the Bi is compared to Bj, it must occur in a recursive call of the algorithm when it is split. Your list LTIC is split into two sublists, and j-tick, your pivot element in line 1 of the quicksort algorithm, it must be one of Bi or Bj out of j minus I plus 1 possible choices. Good. Now your Bi and Bj, they both have equal probability of being chosen as j-tick. So our total probability of random variable, indicator random variable xij to be 1, or in other words, to make a comparison, would be 2 divided by total number of choices, that is j minus 1 plus 1. Good. So that's how this probability P of random variable taking a value 1 comes out to be 2 divided by j minus I plus 1, and then you just solve it. See how simple it was. Now if this line is confusing to you, that the pivot element is being chosen in Bi to Bj, there is another way of thinking it. So you might have seen a dart game. So think about the same thing, dart game. You have been given a dart Bi plus 1 and going all the way up to Bj, and you are throwing an arrow such that it can take any of the values between Bi to Bj. Now if it takes the value Bi, then you are hitting, you are comparing basically. If your z takes the value Bi, you are comparing. As we said, that is the must condition, that either one of the element is pivot element. And you can also say that, okay, if z, this random variable, takes the value Bj, then also you are comparing. But if it takes some value which is in between this, then you are not comparing. You are not comparing with Bi or Bj, right? Because as we said, this is the condition that if Bi and Bj are compared, right? So you can think in that way too. But the the takeaway from this discussion is that when we do analysis of randomized algorithms, we select a indicator random variable, and we try to find out the expected value of number of steps the algorithm will take to give us the final result. In terms of sorting algorithm, we have here the comparisons, pairwise comparisons, right? But you might have some other situation. So idea here is that define an indicator variable which is somehow related to the number of steps or variable your algorithm is going to take, and then you write an equation for the expected value of that and you get the answer. Good. I hope you have enjoyed this short discussion on randomized algorithms. It's a big field, but the idea here is to give you an overview and some sort of insight how to analyze and what are randomized algorithms and so on. Thank you very much, and if you need private lessons, you may contact me at hr@leprofessor.org. If you are facing any difficulty or any problem in this subject, I'm very much happy to help you. Your comments and feedbacks are very much welcome. This helps us to improve the content of the lectures. And thank you for subscribing LeProfesseur YouTube channel. Those who haven't done yet, please subscribe to LeProfesseur YouTube channel and have a wonderful day. Hope to see you again. Thank you.